COMAUNJ series medium payload robots are utilized in SANGRATO's hot forging lines to handle heated metal parts with precision and reliability. These robots ensure consistent part transfer between forging stages, operate efficiently in high-temperature environments, and enhance automation, safety, and productivity in demanding hot forging applications. The Automotive air stamp hammer series, including models such as the HI Blow 35E, Dymax 45E, Newton 13000E, and Newton 30000E, is designed for high-efficiency forging applications requiring substantial impact energy and precision control. These machines operate by pressurizing the upper piston head with compressed air, generating powerful blow energy. The compressed air system also allows rapid and precise vertical movement of the ram, enabling high-speed forging cycles with minimal delay and consistent stroke control. Each unit in the series is equipped with a split-type ram guide, allowing the ram to be disassembled vertically from either side. This feature significantly improves maintenance accessibility and reduces equipment downtime. Additionally, a ram safety catch-lock mechanism is integrated to prevent the accidental fall of the ram due to power failures or system malfunctions, enhancing overall operational safety. The Dymax 45E, in particular, provides exceptional versatility for forging a wide variety of components, supported by its large striking force and responsive control system. The newly developed 45 kJ model extends this performance further, targeting heavier-duty applications. The Newton series models deliver extremely high kinetic energy, suitable for heavy steel and alloy components. Otani air stamp hammers are engineered to deliver consistent, high-energy blows while maintaining control, durability, and user safety in demanding industrial environments. Their advanced design makes them ideal for forging shops seeking reliability, productivity, and long-term performance.
In the heart of Chicago's industrial history stands a true giant of manufacturing, a massive steam forging hammer installed in the 1940s during America's golden era of heavy industry. Towering in scale and built for raw power, this hammer was designed to shape massive steel components with unmatched force and precision. Steam pressure drives its colossal ram, delivering crushing blows that transform red-hot ingots into critical parts for machinery, infrastructure, and wartime production. Each strike resonates like thunder, a reminder of the mechanical might that fueled an entire generation of growth. Forging hammers of this scale were vital for producing ship shafts, locomotive wheels, structural beams, and other components where strength and durability were paramount. The hammer's rigid frame and robust anvil allowed for consistent, repeatable shaping under extreme loads, while skilled operators orchestrated every movement with a balance of strength and finesse. Decades after its installation, this steam forging hammer remains a symbol of Chicago's manufacturing legacy, a monument to an era when American foundries roared with the sound of steam and steel. Even today, its imposing presence and historical significance inspire awe, reflecting the craftsmanship, engineering vision, and industrial spirit that built a nation's backbone. This is not just a machine, it is a living piece of industrial heritage.
HB forging line is designed for efficient and precise production of high-quality forged components. The process begins with heating raw steel billets to optimal forging temperatures, typically between 1,100 degrees Celsius and 1,250 degrees Celsius, to ensure proper metal plasticity. These heated billets are then transferred to forging presses or hammers, where they undergo shaping through controlled compressive forces. The line incorporates advanced automation, including robotic handling and material transfer systems, to maintain consistent flow and reduce manual intervention. Strict quality control measures, such as dimensional inspection and non-destructive testing, are applied throughout the process. This line is suitable for producing automotive hubs, axle components, and other critical parts requiring high strength and durability. The heavy ring blank or gear blank forging process using the Pneumatic hammer Model C 41-2000 kilograms is a precise and robust manufacturing method designed for large, heavy-duty metal components. The C41-2000 kilograms hammer delivers a striking force of 2,000 kilograms, providing the power necessary to deform and shape thick, heated metal billets into ring blanks or gear blanks through repeated, controlled blows. In this process, the raw metal billet is first heated to the appropriate forging temperature to ensure optimal malleability. Once heated, the billet is placed under the hammer, where the pneumatic system drives the ram to strike the metal surface with high impact force. These successive blows gradually shape the metal into the desired blank form, reducing internal defects and improving mechanical properties such as strength and grain structure. During forging, careful control of temperature and hammer parameters is critical to avoid defects such as cracks, laps, or undesirable grain structures. Operators monitor the process closely, adjusting the hammer stroke and energy as needed. Multiple hammer blows progressively shape the billet into the required dimensions and thickness for the ring blank or gear blank. A critical tool used alongside the Anyang hammer is the shingling tongs, specially designed for handling heavy and hot forgings. The shingling tongs securely grip the workpiece, allowing operators to safely and efficiently manipulate, rotate, and reposition the metal blank between hammer strikes. This facilitates continuous forging operations and precise control over the shape and dimensions of the forging. Finally, the forged ring or gear blanks are inspected for dimensional accuracy and structural integrity using non-destructive testing methods before being sent for further machining or finishing. In this vacuum thermos factory, plug components are stamped from 304 stainless steel, prepared for shaping, and then formed using precision dies. Narrow products utilize extruded tube stock, with vacuum tubes press-fitted by a dedicated vacuum machine. Base welding follows, first automatically, then manually for fine finishing. The vacuum processing machine ensures internal insulation through precise evacuation. Each tube passes through grinding, buffing, and polishing stations for a flawless finish. Surface branding includes screen printing, followed by a heat tunnel to cure the ink. For detailed designs, heat transfer printing is applied. The final stages include thorough cleaning, inspection, and careful assembly before secure packing for distribution. The 18L 5-gallon bodyline EMME 1607 is a high-efficiency production system designed for the manufacturing of large metal containers, such as industrial paint or chemical drums. This automated line integrates multiple precise forming and assembly processes to ensure speed, accuracy, and durability in output. The process begins with sheet feeding, where pre-cut blanks are fed into the body forming unit. Here, the blank is rolled and welded longitudinally using high-frequency resistance welding. The welded seam is automatically inspected and cooled before the next stage. The welded shell then proceeds to the flanging unit, where the top and bottom edges are precisely flanged to allow lid and base assembly. Following flanging, the body moves to the lid feeding station, where a lid is placed precisely on top and sealed using a double seaming process. Afterward, the drum is conveyed to an automatic inverter, which rotates at 180 degrees, positioning the bottom side upward. At the next station, the bottom cover is fed and aligned onto the open end of the body. Another double seaming machine seals the bottom, completing the assembly. Finally, the finished drums are grouped by workers, who manually tie them together in sets of 6. This bundling process ensures easier handling, organized stacking, and efficient transportation to the next stage, whether it's storage, inspection, or delivery. Each bundle is securely fastened with plastic straps or durable twine to maintain stability during movement. This robust line can produce hundreds of units per hour, delivering consistent quality for industrial-grade metal packaging.
An 8-station progressive stamping die is used to produce custom brackets from 18GA galvanized steel. The process runs on a 110-ton Komatsu punch press, performing multiple precise forming and cutting operations across 8 stations. This setup ensures high efficiency, consistent quality, and fast production for complex metal parts. The progressive metal stamping die process begins with feeding metal sheets into the progressive stamping press. The die performs sequential cutting and forming operations on the metal. After stamping, parts pass through an inline deburring stage, often involving a vibratory tumbler to remove burrs and smooth edges. Quality checks follow to ensure dimensions and surface finish. Finally, finished parts move to an automatic packaging system, optimizing efficiency, reducing cycle time, and ensuring consistent product quality.
In the heart of Toyota's manufacturing line, raw steel transforms into precision-crafted panels within seconds. This is the world of high-speed stamping, where force meets finesse, and every press shapes the future of mobility. Toyota's stamping process forms the structural panels that shape each vehicle's body shell. It begins at the blank receiving station, where flat metal sheets, called blanks, are inspected for quality before being conveyed to the press line. Each blank is carefully handled to prevent defects during transfer. The appropriate die set, depending on the vehicle part being produced, is selected and lifted into position by overhead crane. The stamping press, a massive hydraulic machine, then applies high pressure to form and cut the metal into specific automotive panels. General maintenance teams oversee equipment functionality, performing regular inspections and servicing to keep the machinery in peak condition. Formed panels move along conveyors for visual and dimensional inspection. Additional quality control checks are conducted in designated highlight areas. Approved parts are hand-loaded into pallets, conveyed to storage zones, and tracked for inventory. Toyota integrates quality assurance into every step to meet rigorous production standards.
Martinrea Industrial Canada's Project V repurposed its Ontario hydro-formed subframe line to mass-produce ventilator stands for GM within 6 weeks of project launch. Engineers converted an existing 800-ton servo press and 5-axis laser cell to form and trim 2mm 304 SS tube uprights, while a dual-spindle CNC router milled 6,061 T6 base plates to plus or minus 0.08 millimeters. Robotic GMAW cells with pulse spray transfer joined the assemblies, using fixturing adapted from seat frame welding nests to hold plus or minus 0.5 millimeters datum accuracy. Inline eddy current probes verified weld penetration on every part. A powder coat line running low-bake epoxy polyester cured at 160 degrees Celsius prevented temper loss. Automated packaging islands completed kitting, enabling output of 30,000 units in 25 days, meeting GM's accelerated ventilator schedule and demonstrating Martinrea's agile manufacturing and vertical integration capabilities during the COVID-19 crisis. The Simpact Tandem press line is a critical asset in the automotive industry, enabling high-efficiency, large-scale production of precision metal components. This advanced system integrates multiple presses working in sequence to form complex parts like body panels, chassis, and structural elements. Featuring automation, high-speed operation, and robust die systems, it ensures consistent quality, reduced cycle times, and cost-effectiveness. Simpact's technology supports just-in-time manufacturing, meeting stringent automotive standards for safety, durability, and performance, while optimizing production flexibility and scalability.
Voltran specializes in the high-precision engineering and production of power and distribution transformers ranging from 150 kVA to 100,000 kVA. Key manufacturing steps include silicon steel core cutting, precision coil winding in copper, vacuum resin encapsulation, and complete dielectric testing. Final products include pedestal, substation, dry type, and resin encapsulated transformers. All systems are optimized for performance, durability, and grid efficiency. The mold splitter is a specialized machine designed for the safe and efficient handling of plastic injection molds. It features a large upper table and a sliding carriage with adjustable parallels, allowing flexible positioning of various mold sizes. A key component is the 5-ton tilting system integrated into the lower frame. This tilting function is essential for ergonomic work on half molds and for vertical positioning during assembly or disassembly, as typically required in injection mold setups. Molds are secured using powerful permanent magnets, enabling fast and tool-free clamping. An extra mechanical safety stopper adds a layer of protection during rotation. The operator can rotate the mold easily and lock it in any desired position without effort, using the mobile control interface. The machine's hydraulic handling system ensures smooth and synchronized movements, while the integrated software halts operations immediately in the event of a malfunction. In under 2 minutes, users can complete the mold loading, magnetic clamping, and tilting sequence. The machine provides unobstructed access to mold components for maintenance or fine-tuning. It also includes customizable utility ports and safety interlocks, ensuring optimal operational safety. This system supports efficient mold preparation and setup, reducing downtime and improving workplace ergonomics. Ideal for modern injection molding facilities, it delivers a balance of power, precision, and safety for mold management tasks.
In the heart of railway maintenance and manufacturing, precision and strength come together in the wheelset press mounting machine, a powerful system designed for assembling and testing the wheel sets of passenger cars, wagons, EMUs, and city rail vehicles. Its primary function is to press fit and withdraw wheels, brake discs, and gear wheels with absolute accuracy, ensuring every component is perfectly aligned and securely mounted. Whether it's standard gauge, meter gauge, or broad gauge, this machine adapts effortlessly to diverse railway specifications. Built with heavy-duty hydraulic systems and advanced control technology, it delivers the exact pressing force required, neither too little to risk loosening, nor too much to damage components. The result is a flawless fit every time. Beyond assembly, the wheelset press mounting machine also performs anti-pressure tests, verifying the structural integrity of the wheelset under extreme loads. This ensures every wheelset meets stringent safety standards before it hits the rails. Its automated measuring systems record pressing force, displacement, and positioning data, providing a digital quality report for every operation, an essential feature for modern rail safety compliance. From initial mounting to precision testing, every step is controlled, monitored, and documented. Operators benefit from intuitive interfaces, robust safety features, and the ability to handle high production volumes without compromising on accuracy. Strong, reliable, and engineered for the future of rail transport, the wheelset press mounting machine plays a vital role in keeping trains running smoothly, safely, and efficiently, ensuring that every journey begins with perfectly assembled wheels. Kobelco offers an advanced welding robot system designed for high-quality, automated structural steel fabrication compliant with AWS D1.8 standards using FCA WMX50R wire. The system streamlines welding with features like automatic wire cutting, slag removal, and sensing functions, enhancing efficiency and precision. The operation begins by mounting the workpiece on a positioner. Operators input measurements and details via a PC interface, where welding conditions and weld paths are automatically generated based on the data. This system is ideal for various industries, including shipbuilding, railroad car fabrication, construction machinery, and large assembly welding. Key components include the Kobelco ARCMANTMP arc welding robot, powered by the SEN-SARCTAB 500 power source, capable of 100% duty cycle at 450A non-pulse, or 400A pulse. The slider offers a wide traverse stroke of 18,000 mm LR and 2,000 mm BF, while the positioner supports a maximum load of 15,000 kg. The welding wire used is Kobelco FAMIL Atli AR CTM-MX50R, compliant with AWSA 5.20 E70T1C and AWSD 1.8 standards, shielded by 100% CO2 gas. During operation, the system enables easy remote input of workpiece data and begins robot welding with wire touch sensing. It ensures stable welding arcs, low spatter, and automatic tool changes from welding torch to slag removal. The positioner rotates the workpiece to optimal angles, and the system includes automatic nozzle and torch cleaning, with wire cut to an optimal stick-out length. This results in efficient, precise welding of base plates, stiffeners, and shear plates.
The welding phase in the H-beam welding machine process is the most critical and technically demanding step. After the web and flange plates are positioned to form an H configuration, the beam is moved into the welding station. Here, submerged arc welding (SAW) is employed due to its high deposition rate, deep weld penetration, and excellent mechanical properties. The process begins with the assembly of 3 steel plates, 1 horizontal and 2 vertical, which are automatically positioned and held in place by a hydraulic alignment system. These components form the initial H shape. Two saw torches are mounted on a gantry system, positioned on either side of the vertical web. These torches operate simultaneously, welding both sides of the beam in a single pass. The SAW process involves a continuously fed wire electrode and a layer of granular flux, which covers the arc zone. As the arc melts the wire and base material, the flux forms a protective slag that prevents contamination and helps shape the weld bead. Automatic seam tracking systems play a vital role during this step. These sensors monitor the joint line and make real-time adjustments to the position of the torches, ensuring perfect alignment even if the plates are slightly misaligned. Welding speed, current, and voltage are precisely controlled through a central PLC interface, optimizing penetration and minimizing heat-induced deformation. To maintain welding quality, flux recovery systems are installed to collect and recycle the unused flux. The slag formed after welding is removed manually or mechanically before the beam proceeds to further processing. This dual-pass saw operation guarantees strong, uniform welds along the entire beam length. The resulting welded joints meet structural integrity requirements for heavy-duty applications in building frames, bridges, and industrial platforms. The process minimizes human intervention while ensuring precision, speed, and repeatable welding quality. The DEP 200 by 5000 dish end press with manipulator is a robust, steel-welded hydraulic machine designed for dishing, bending, and straightening tank bottoms or various plate components. Its thermally stress-relieved frame ensures durability. The press features an automatic manipulator for efficient plate movement, a hydraulic power station with motor pump group, oil cooler, and adjustable piston for different radii. All rotary movements are hydraulically driven, while translation is managed by hydraulic or electromechanical actuators. The system includes limit switches, pressure valve, manometer, and a user-friendly electric control panel.
In the
Hot bending process is a precision technique used to transform straight steel pipes into curved bends while ensuring dimensional accuracy and structural integrity. The process begins with the receiving of the mother pipe, where raw pipes are inspected for compliance with material specifications. Next, the pipe is cut to the required length for the bending process. The cut section is heated in a controlled furnace to reach the required temperature for plastic deformation. During heating and bending, careful monitoring is conducted to maintain uniform temperature distribution. After forming, ovality is adjusted to ensure the pipe's cross-section remains within tolerance. The pipe then moves to the dimension check table, where all critical measurements, bend angle, radius, diameter, and wall thickness, are accurately recorded and documented. Following this, heat treatment is applied to relieve residual stress and restore mechanical properties. To ensure product integrity, both non-destructive tests like magnetic particle inspection and ultrasonic testing, and destructive tests such as tensile or flattening tests are conducted. Finally, end beveling is performed to prepare the pipe ends for welding. Every step is recorded for traceability and quality control compliance. The Olympic Solar specializes in advanced solar technology, offering high-efficiency thermal collectors, hybrid PVT panels, and durable mounting systems. Engineered for maximum heat absorption and minimal energy loss, their systems feature precision manufacturing, corrosion-resistant materials, and optimized fluid circulation, ensuring long-term performance and reliability in diverse climatic conditions. The GMO solar collector features a high-performance absorber coating with absorptance is greater than or equal to 95% and emissivity 5%. Made with polyester staple fiber and eco-friendly corner protectors, it ensures durability, prevents leakage, and safeguards the glass cover during transport and installation, providing reliable, long-lasting solar energy collection. The new Mill 4-15 platform from Kennametal is engineered for best-in-class shoulder milling performance. Featuring a double-sided insert with 4 cutting edges, the Mill 4-15 offers exceptional cost efficiency and extended tool life. It supports depths of cut up to 15.5 millimeters, 0.61 inches, making it ideal for a wide range of roughing and finishing operations. The Mill 4-15 is highly versatile, with multiple corner nose radii and universal insert geometries, suitable for materials like 42 CRM04 steel. Tested speeds and feeds include cutting speeds up to 180 meters per minute, feed per tooth of 0.15 to 0.18 millimeters/rev, and axial depth of cut from 3 millimeters to 12 millimeters. This platform excels in full slotting and variable width applications, delivering a powerful solution for high-performance milling in demanding environments. This CNC mill-turned machining demonstration showcases the advanced capabilities of Step Rapid's integrated turning and milling centers. The steel billet is fed into the machine. Using a precision center drill, the machine creates a shallow conical hole at the exact center of the workpiece. This initial step is crucial as it provides an accurate starting point for subsequent drilling and turning operations. Center drilling ensures precise alignment, prevents tool wandering, and enhances the accuracy and concentricity of deeper machining steps that follow. Immediately following, without the need for repositioning, live tooling executes complex milling operations, such as flat surfaces, keyways, and drilled features, on multiple axes. Step Rapids machines utilize synchronized spindles and sub-spindle transfer to machine both ends of the component seamlessly. Tool changes are automated and rapid, minimizing downtime. With tight tolerances and smooth surface finishes, this hybrid process is ideal for complex parts requiring multiple operations in one setup. These machines are optimized for high-mix, low-volume production in aerospace, automotive, and medical applications.
Okuma's Genos L250 CNC lathe delivers rigid precision on a one-piece cast iron bed with horizontal boxways and hand-scraped headstock/tailstock seats. The compact 30-square FT footprint supports 6 or 8-inch chucks, 18.5 and Z-travel, and high-speed spindle options, providing cost-effective entry-level turning capability without sacrificing accuracy or throughput. Rough turning is performed using a Sandvik Capto-modular tool holder paired with a Corloy CNMG 432 LP 3515 carbide insert, delivering high rigidity and precision under demanding cutting conditions. The Sandvik Capto system ensures secure, vibration-resistant clamping, allowing stable operation at high material removal rates. The CNMG 432 LP 3515 insert, with its advanced coating and optimized chip breaker geometry, offers excellent wear resistance and efficient chip evacuation, even in tough alloys. This combination enables aggressive cutting parameters while maintaining consistent surface integrity and tool life. The setup is ideal for heavy-duty operations where dimensional accuracy must be preserved during large stock removal. The system's modularity allows quick tool changes, minimizing downtime, while the insert's design reduces cutting forces, enhancing spindle load efficiency. Suitable for various steels and stainless steels, this pairing delivers cost-effective, repeatable performance in roughing cycles for both manual and automated turning applications. Precision engineering meets advanced dry cutting technology in the manufacturing of the Bevel Gear M5.5 Z22. Designed for high-load transmission systems, this gear features a module of 5.5 and 22 precisely machined teeth, ensuring smooth power transfer and minimal vibration. The dry cutting process eliminates the need for cutting fluids, reducing environmental impact while maintaining exceptional dimensional accuracy. Specialized coated carbide tools operate at optimized speeds, producing clean tooth profiles with superior surface finish and consistent geometry. Advanced CNC gear cutting machines execute precise indexing and profile shaping, ensuring perfect alignment between mating gears. Heat-treated alloy steel provides high tensile strength and wear resistance, extending operational life under continuous load. Ideal for heavy-duty machinery, automotive differentials, and industrial gearboxes, the Bevel Gear M5.5 Z22 delivers reliability, efficiency, and performance, engineered to meet the most demanding mechanical requirements. Using profit milling on a Mori Seiki NVX 5080 slashes, cycle time from 52 minutes to 14 minutes, while boosting tool life over 500%. A 20mm Paul Horn end mill rough CK45 aerospace stock at 6,000mm min, 0.38mm FZ, 5,000 revolutions per minute. With a 25% engagement angle and 35mm axial depth, the strategy maintains constant chip load, minimizes heat, and maximizes spindle efficiency.
The MAAG SH150 gear shaper precisely machines a 24-module, 22-tooth gear using a single-point cutting tool. This process involves indexing and reciprocating cutting strokes to shape each tooth profile. During operation, coolant is continuously sprayed into the cutting area to reduce heat, wash away metal chips, and maintain accuracy.
Okuma's LB3000EX horizontal lathe combines thermo-friendly concept casting with a slanted boxway bed to suppress thermal drift and vibration, ensuring micron-level repeatability. A 22/15 of a kilowatt Prex spindle drives JISA 26 nose from 45 to 5,000 revolutions per minute, handling heavy hogging and high-speed finishing alike. The platform offers E410mm maximum swing and up to 1,300mm Z travel, with rapids of 25 meters min X and 30 meters min Z for fast positioning. Configurable options, live tooling, Y-axis, subspindle, and multiple bore sizes extend the machine to full turn mill capability. Open architecture OSP page CNC simplifies automation integration, making the LB3000EX a rigid, thermally stable solution for diverse production requirements.
In a tightly integrated metal casting workflow, the production of a carburetor adapter begins with traditional sand casting, followed by precision machining to meet strict dimensional tolerances. The process starts at the foundry, where a wooden or 3D printed pattern of the carb adapter is used to create the negative cavity in a split mold. The pattern includes allowances for shrinkage and draft angles to facilitate clean release from the sand mold. The sand, often bonded with oil-based or sodium silicate compounds, is tightly packed around the pattern within cope and drag boxes. Once cured, the mold halves are separated, the pattern is removed, and the gating system, sprue, runners, and risers, is carved in. Molten aluminum, heated to over 700 degrees Celsius, is poured into the mold cavity. As the metal fills the void, risers compensate for volume reduction during solidification, ensuring the casting remains free of internal voids. After cooling, the sand mold is broken apart and the raw casting is removed. Risers and excess flash are trimmed off, and the casting undergoes shot blasting to remove scale and provide a uniform surface. The raw casting is then transported to the machine shop. Fixturing is critical at this stage to align the casting for accurate machining. A CNC vertical mill, or a manual Bridgeport-type machine, is used to machine all functional surfaces. First, the base flange is surfaced flat to ensure a tight seal when mounted on the intake manifold. The bolt holes are spot drilled, then drilled to depth and tapped with precision. Carb mounting holes are drilled in a specific pattern and chamfered for proper hardware fit. The central bore is bored and optionally port matched using a rotary table to match the engine's intake runner dimensions. The adapter is often test fit on a carburetor to ensure clearances and alignment are perfect. In some cases, additional operations such as anodizing or powder coating are applied for corrosion resistance and appearance. Through a combination of robust foundry techniques and precision machining, the carb adapter is transformed from raw aluminum into a functional, high-performance engine component ready for installation. This blend of casting tradition and modern milling ensures both structural integrity and dimensional fidelity. The production of Agro Bearings BBCR begins with the creation of a 3D model based on technical drawings. Casting partners manufacture high-strength iron blanks with a specified chemical composition and verified metal hardness. These blanks are transported to the machining facility in Rezekne. Before machining, each casting undergoes powder coating in a dedicated paint chamber, followed by curing in an oven at 150 degrees Celsius for 1 hour. Precision turning is then carried out on the bearing housings. Visual and instrument-based inspections ensure dimensional and surface quality. Completed housings are sent to the assembly plant in Riga, where bearings are installed. Each bearing unit is individually packaged and prepared for delivery to customers.
At VMB, valve production follows a tightly sequenced, vertically integrated workflow. Engineers begin with 3D design and solid flow casting simulation to optimize gating. Wax patterns are produced by high-pressure injection, then chased, gated, and ceramic dipped to build a refractory shell for the lost wax process. After dewaxing, shells are sintered to full strength, and alloy is melted in an induction furnace and poured under inert gas. Once solidified, the ceramic is knocked out, gates are removed, and castings pass shot blasting and solution heat treatment. Statistical quality control, spectrometry, UT, and dye penetrant precedes CNC machining of bodies, bonnets, and internals. Finished components are assembled with precision lapping of seats and plugs, followed by hydrostatic and pneumatic pressure tests to API standards. Finally, valves receive anti-corrosion coating in a controlled paint booth, cure in a bake oven, and move to final inspection and packaging for worldwide shipment. The iron steel lost foam casting production line for steel tube molding utilizes a customized solution to ensure high precision and efficiency. The process begins with the creation of polystyrene foam patterns, which serve as exact replicas of the final steel tube components. These foam patterns receive a refractory coating that provides thermal resistance during the casting process. Once coated, the patterns are carefully heated in an oven to remove any residual moisture and prepare them for molding. The next step involves placing the coated foam patterns into flasks, which are then filled with sand. The sand is compacted around the patterns using a vibration table to ensure stability and accurate shape retention. Pouring basins, runners, and risers are glued to the assembly to facilitate smooth metal flow and gas escape during casting. Molten metal is then smelted and poured into the mold, where the foam pattern vaporizes, leaving a cavity that the metal fills. After solidification, the empty castings are removed from the flasks and transferred to storage. The castings undergo shot blasting to remove any surface impurities, resulting in finished steel tube components ready for further processing or shipment. This integrated production line guarantees consistent quality and efficiency in steel tube manufacturing. The
A
lost
flat aluminum disc becomes a precision-engineered wind vane nose cone through the high-skill process of metal spinning. The operation commences by securely clamping the disc onto a rotating mandrel, shaped precisely to the inner profile of the final nose cone. As the mandrel spins at high speed, a skilled technician applies steady pressure using a forming roller or spinning tool. The aluminum begins to flow over the mandrel, gradually adopting its contour without removing material, a hallmark of this chipless, cold-forming process. The process continues with successive passes of the roller, refining the curvature and thinning the metal as needed to achieve uniform wall thickness. Critical parameters such as rotational speed, tool pressure, and feed rate must be precisely controlled to prevent wrinkling or tearing. The metal's ductility allows it to conform without cracking, while internal stresses are minimized through even deformation. Upon completion of shaping, the part is trimmed to exact length, and the nose cone is removed from the mandrel. Surface finishing operations, such as polishing or anodizing, may follow, depending on design requirements. This efficient forming technique produces strong aerodynamic components ideal for lightweight assemblies, such as meteorological wind vanes. Sheet metal forming and bending involves shaping metal sheets into desired geometries using processes like pressing, folding, and rolling. Precision machines apply force to create clean, accurate bends and curves. Common applications include panels, enclosures, and brackets used across automotive, HVAC, and construction industries. The RAS 12.35-2 Easy Former is an intelligent swaging machine designed for precision and operator safety. Equipped with a divided stop plate and insulating stop, it ensures stable workpiece positioning and insulation during operation. The system supports variable speed and step adjustment, allowing fine control of material feed. A second foot switch enhances workflow efficiency, while the machine enables quick direction change and function setting. These features make the RAS 12.35-2 ideal for flexible, high-quality forming tasks in sheet metal processing.
The JUTEC Billet System 5000 is an economical, electrically driven tube bending machine designed for tight bending radii and versatile production demands. Featuring a freestanding bending head, it allows quick conversion between right and left bending, with plug-in tools enabling rapid changes for various tube sizes. APLC control with X2X interface stores up to 50 bending sequences per tube and 200 material profiles, ensuring precise springback compensation. 2 operating modes, simple and controlled bending, provide real-time positioning checks to minimize errors. Adjustable clamping pressure, programmable mandrel retraction, and fast hydraulics enhance efficiency. Available in mobile or stationary versions, it supports diameters from 6 to 50 millimeters, bending radii from 10 millimeters, and up to 180 degrees bends. Applications include hydraulic piping, pipeline construction, plant engineering, and metal fabrication, offering a cost-effective alternative to fully CNC-controlled machines.
Rinke Sheet Metal Working Machines specializes in precision solutions for sheet metal processing. Their machinery lineup includes bending machines, shears, notching tools, and punching systems designed for high productivity and accuracy. These robust and reliable machines are suitable for manufacturing ducts, panels, enclosures, and various industrial components. With advanced control systems and ergonomic designs, Rinke machines ensure efficient operation, minimal setup time, and consistent results, making them a dependable choice for both small workshops and large-scale metalworking facilities. A 130 millimeters thick steel plate is being rolled into a perfect cylinder by a MAV 3-roll variable axis plate roll. With 4,000 tons of bending power, this machine delivers exceptional performance, minimal flat ends, and high productivity, ideal for pressure vessels, heavy fabrication, and industrial applications.
Combined physical compression tests and FEM revealed that final forge integrity of large heads depends on anvil geometry and thermal mechanical coupling. Flat anvils promote homogeneous shear flow, while crowned anvils elevate triaxial stress at fillets, fostering radial cracks. Optimal process windows: 150 degrees Celsius finish temperature, 0.7 strain rate, and progressive die radius transition. Minimize void coalescence and ensure isotropic grain refinement.
The Davy MCP 3-roll angle roll is designed for heavy-duty profile bending, including hardware H-beams up to 320 millimeters. It delivers precise results even on large, non-standard profiles, making it ideal for aerospace, shipbuilding, automotive, and structural applications requiring tight diameters and strict tolerances.
On the milling machine, the DN450 ball valve body takes shape with precision engineering. The cutting head moves methodically, removing layers of metal to form the perfect spherical contour required for flawless sealing performance. Each pass is calculated, ensuring tight tolerances and a smooth surface finish. This meticulous process is essential to the valve's durability and efficiency, enabling it to withstand high-pressure flow conditions in industrial applications. From raw casting to refined component, precision defines every step.